What's on the bench today? It's a vacuum tube voltmeter by Weston. Quite a rare one according to what I know. Anyway, one of my finds. Know nothing about this thing. I did find a few little things online. I did give it the quick check. And the only way to check it is you give it a good shake and the meter still moves. However, there is something clinking around in there. One little bitty tube in here is from the schematic. So old it's got the old jack pickup there. I got one of those. Happened to have one of those like that. That's another pickup. Very useful tool when doing vacuum tubes. However, this one's quite rare. Ugh. Serial number 215 was only ever made for a year by Weston. Never produced again. Like I said, I found that one article that some guy gave me online and a schematic, which is good. Let's open it up first time here and see what's on the inside. I think this is what opens. This is battery powered, and it's supposedly good for 1 full year on the battery. May not have the right size. Ah, there we go. That's one. We'll see. It could be all scrap inside. It might not be worth anything. You'll know as soon as I do. Probably only about 1,000 less than these made for the entire North American market. So it's probably the only one you're ever going to see. Quite the find. Like I said, the old guys said they'd never seen one. Let's see what's inside. Will it be nothing but batteries or rust? Oh! It's nice and clean inside. There's the battery hookup. There's the tube. Ooh, that is clean on the inside. There's the C battery there. That's what's rattling around. Probably won't take much to get this going again. Meter plus, meter minus. I have to figure out a... Yeah, it is clean on the inside. Precision resistors. There. Ooh. Very early film caps. I don't have to think about. There's the tube. It's still in good shape. This is the battery terminals. So it takes 2 big batteries there. And I think that's just the regular battery in there. I'm not sure which goes where. So it's probably a big battery goes on there. Links across maybe? Don't know. Don't know. It's 45 volts, so I can use a bunch of 9-volt batteries in a pack. It should work. Looks like the front meter panel comes off. I could take these off. Let's get the front panel off and see what's on the other side. While I'm busily taking off the front panel, I'm going to take this opportunity to review how this VTVM, and probably most others, actually work. Here's the schematic once again. As you can see, it's pretty complicated for a box that doesn't have a lot of parts in it. Fortunately, that article I found gave me all the basic info I needed to figure out what's going on. It seems that my Weston meter is just a variation on a Wheatstone bridge. Now that brings up the next question: what exactly is a Wheatstone bridge? Well, the Wheatstone bridge is most likely the oldest circuit design that's still in common use today. It was first described by a chap named Samuel Hunter Christie in 1833. About 10 years later, in 1843, Sir Charles Wheatstone improved upon it and popularized its use in telephony. I guess by the 1840s there were plenty of practical applications for the circuit, and I guess his name just stuck ever since. In its simplest form, we start with a voltage source, and we connect that to a diamond-shaped network of 4 resistors. And we connect between the parallel sides of these resistors a galvanometer. Now, if all 4 of our resistors are of the exact same value, the needle of the galvanometer will stay dead in the center. This is because the current flow through both branches of the circuit is perfectly balanced. Now that the bridge is balanced, we can swap out one of the known resistors for a resistor of an unknown value, and immediately our galvanometer will deflect, indicating that the circuit is now out of balance. To bring it back in balance, we simply added more resistance on the adjacent side of the unknown resistor until the galvanometer needle returns to the middle. Now, using this simple formula and a little arithmetic, we can calculate the value of the unknown resistor. So that's the 25-cent tour of the Wheatstone Bridge. If you want more detail on bridge circuits, check out Curious Marc's recent episode on the Leeds and Northrup 4398-M resistor board. It's the mother of all resistor bridges. I left a link for it in the description below, and if you really like to dive into the math side of things, check out the Organic Chemistry Teachers video, which I also left a link for below. Looks like I have the front panel off now, so let's head back to the bench.
Oh, here's the outside. Managed to, actually you don't need to take anything off to see on the other side. Fortunately, you look over here, it looks like it's been repaired. That doesn't look original. Zoom in on that. Yeah, that looks like a repair or something. Really old. Get off-gassing here. So I wonder, off-gassing here, this is somebody put these in, I think, to stop it from, yeah, that doesn't look original. Could be. Could be original. Yeah, they're stuck pretty good. Stop any shorting in there. Put them back in. But definitely needs a good cleaning. There's off-gassing there. Could be factory, that. Hard to say. Or someone swapped out these modern caps for the old ones. Let's see, 75 volt, 600 volt DC. Yeah, maybe this is a swap out. Ooh, a swap out at a later date. Yeah, could be. Like I said, everything else looks original, but you know, someone's been in here mucking meter plus. That's definitely not factory. Oh well. Gonna give it a good clean, I think. That's definitely been mucked. That wouldn't come. This wouldn't come out of the factory like that. Definitely not. Okay, let's give her a good clean. Ooh, a lot of grime. That's set for a few minutes. Get rid of all this grime.
As I mentioned earlier, the board turned out to be a lot dirtier than I originally thought. So while I'm busily cleaning that up, being very careful not to rub off any of the lettering on the back side of the board, let's have another look at the schematic. Like I said before, the schematic's a little daunting, and I can clean that up a bit by getting rid of all the marginal notes. And that only leaves me with trying to figure out what the switching system does. Looking back at the front of the meter, we know that we have 2 switches, one labeled range and the other function, and they correspond to S1 and S2. We also have 2 jacks on the front, and a 0 and an ohms adjust knob. Going back to the schematic, the ohms adjust and the 0 adjust are both clearly labeled, but there's also these 2 variable resistors here, R22 and R21, AC and DC. I did manage to locate those 2 resistors, and it's this one and that one. As these are most likely factory presets, we can just ignore them for now. There's also a couple of variable caps, and like the other two resistors, they're factory set, so ignore those as well. Now the first thing I did was come up with a block diagram, and it wasn't too particularly difficult. First there's this input section. Next there's the range, or as I like to call it, the attenuation section, and the function section. Now with a block diagram and a general idea of what part of the schematic does what, let's have a closer look at the attenuation section. Now the switch has 7 positions, and as you notice there are 3 tabs in the switch. And it is these 3 tabs that determine what the exact path will be from the input block and into the function block. Now the function switch is a little more complicated. Not only does it have 6 stops, it also has 5 tabs and controls both the input block and the function block. Now here are the 6 positions: off, DC, DC negative, ohms, point to point, and AC. I'll put it back into DC and we can have a quick look at what's going on. Now the first tab on the left is setting the input network. And in DC mode, we start at the top of the attenuation network. The next tab determines the path to the grid of our cute little valve. The third tab hooks up the heater to the 1.5 D cell. And the final 2 tabs hook the meter into the circuit. Let's have a detailed view of how these 2 switches work together. So let's start with the attenuator set at 1x, and then put the function switch into DC positive. And as you can see, the resultant path of the input signal to the grid is through R1 to R8, then R16, and then the grid. There is also this capacitor C8, which will bleed off any AC that might interfere with our measurements. As I was finishing off the cleaning of the circuit board, I also decided to take off the switches to clean underneath them, and then I discovered this.
So just playing around here, and I was wondering why I wasn't getting any connection, and there's the reason. The switch is all busted up. Ooh, that's going to be nasty to put back together because I don't know how it goes. I'm not sure if that happened when I took it apart, or it's been like that for a while. It looks like it's been like that for a while actually, because the other one looks in good shape. So let's get that off and see if we can get that all put back together correctly. I think I'll take this off though. What we have here is electronics archaeology. I've got to figure out how this works. As we saw before, this thing broke off, and I managed to put them back on there. Of course, all I did was put a little plasticine under them so they fit. We flip her over. And you can kind of figure out how I finally, after diddling a long time, got it all lined up. There. You can see right there. Zoom in a bit. There are 3 lines there. 1, 2, 3, 4, 5. There's 5 positions. 1, 2, 3, 4, 5, and 6. Well, 6 positions. And that lines up, and all the other ones line up correctly as well. So I'm going to have one shot to put that back together. I'm going to take a little epoxy and glue those back on the way I've got them orientated. And I kept the orientation the same. And I'll do the same on the other one on the other side. And you can see, with the macro version, we've got a couple trace cracks. Whoever had this first decided to put more trace down for whatever reason. I don't know. That does not look original. I'll have to fix that trace here. And looks here. And I'll put some more on that, some cleanup on these because they're cracked. The actual board is cracked. Taking a very close examination. That's about it for now. I will swap out these ones for some newer ones, I think, and I'm going to get rid of that one. Not sure about these resistors here. They all have to be within spec, and these 2 caps will probably have to go as well, but we'll see. First thing I'm going to do is, I'll zoom out again, is I've marked where all these pots go. red on red. Same thing on that. I'm going to clip these out so I don't have all these dangly wires all over the place, and I'll do the same thing over here with this battery holder. Believe it or not, they still make batteries for these, well, at least the 22 volt ones, but we'll worry about that later. I'll start with the clipping. Let's see, where's my clippers? As usual, I'm going to leave a little bit of the tail end right there, so I know what color goes where. And as I've got more than one wire, I'll mark this wire with a little red, so I know where it goes. Alright, that's all put away. Now that's a little easier to work with now. Let's get those traces fixed up first. Alright, get set up for that. To fix that trace, I keep a little bit of this tinned copper plate around. So I'm just going to cut something to the right size to breach that gap and to breach that gap, and then paste it in. The only thing you have to be careful is you have to make it very smooth, because you don't want to bump when that, I guess it's called actuator? Yeah, it's an actuator, goes over top, or the pad, I guess it's a pad in this case, runs over top. You don't want it to get caught. So I have to be very careful on the size that I make it. Let's get that done.
And as I'm busily fixing those traces, let's go back to the schematic and figure out how this voltmeter works. So the first question is, what have we changed in our Wheatstone Bridge? Now, one of the nice things about the Wheatstone Bridge is it can be set up in many different configurations, all working basically the same. So in our configuration, while we're not using a galvanometer, which measures both current flow and current strength, we're going to change that for a voltmeter that just measures volts in one direction. Now, instead of using a resistor for one of our adjacent sides, we swap that out for a positive to negative voltage. And we do the same for the other side. And we replace one of our resistors with a vacuum tube. Now remove the negative lead of our unknown voltage from the junction at the bottom of our two resistors to the junction of the two 22.5 voltages. Finally, remove the positive side of our voltage and attach that to the grid of our valve. Now, the panel meter they selected for this voltmeter has a range of 0 to 1.6 volts. And that's the full range of this voltmeter. And that's where this attenuation network comes back into play. It always tries to keep the voltage going on the grid between that 0 and 1.6 volts. Now, there's still a few little key components we have to add in, so I'll just move things around here a little to give me a little more room to work with. Next, I add in the heater voltage, and what that's going to do is going to throw our meter off balance. Now, if you go back to the schematic, you'll see that R23 and R21 are a voltage divider, and that's used to balance the valve at 0 from the factory. Now, batteries, of course, get weaker over time, so to compensate for that, we add in R18, the zero-adjust variable resistor. Now, if we put a voltage of 0.8 volts across our leads, our voltmeter is going to deflect halfway, and we just read the voltage off the scale. Now, what would happen if we had 80 volts across our leads? Well, the first thing you would have done was set the range to 160, and you get the same deflection. Now, if you made the silly mistake of leaving the range on 1.6, all that's going to happen is the meter is going to spike at its maximum value of 1.6 volts. This is why these old vacuum tube voltmeters are so indestructible. There's no physical connection between the grid and the plate, just a wire mesh suspended in a vacuum. The designers also slightly negatively biased the grid by adding in that 22.5 volt battery here, with the positive side on the ground rail and the negative side on the zero-adjust voltage divider. And when running like this, our grid basically draws no current from the circuit you're looking at. The DC voltage also runs through R16, which is a 33 meg resistor. So no matter what the voltage, we're always going to draw very little current. So if one did try to measure 1600 volts DC with the range at 1.6, you're only going to draw about 50 microamps of current. Not enough current to hurt anything in the voltmeter. And that's how the positive DC works on this meter. To measure negative DC, the switch simply reverses the polarity of the voltmeter and reuses the same circuit. Looks like I'm all done doing the traces, and I'm just checking the continuity, so let's get back to the live action.
To here, and to here. I think that's good. Hey! Well, that cleaned up nice with a bunch of deoxit. And now, I'm going to have to put this thing back together. I have exactly one chance to glue it correctly. And I probably have to glue everything down because they're all pretty loose. Some of them are moving by themselves. See, that one's actually part of it, but it's actually loose. So, what I'm going to do is a little experiment with this one over here. And I'm going to try to glue a piece of metal, similar type, on there with some epoxy I have that's supposed to fit. So I'm going to make up a little bit of epoxy, glue it on there, and see if it'll actually hold to it. If it doesn't, I'll have to take the drastic thing of actually remelting plastic across that, a plastic bar or something across there, and mold it into the plastic. Bringing back some of my modeling skills from 40 years ago. First I got to clean that up because I touched it with all sorts of goop as I was playing around. Anyway, we can go try that epoxy trick now.
Well, the next little bit is just me mixing up glue and putting that little copper tab in place. So I think it's a good point to stop this video, as I've droned on long enough. But don't worry, there'll be a part 2 and I still have lots of other things to do, like make a probe, get some sort of battery pack for this system, and make sure the whole damn thing works. So stay tuned for part 2.